Okay, so good afternoon. So this is the final lecture of Chapter 4, to be precise, Lecture 7 in Chapter 4. And what we are going to do is we're going to start with a slight review of a brief review of what we covered in the last lecture, which I thought was an important lecture. So if you missed it, please make sure you follow up what was covered in class. Okay. So what we really talked about is we kind of integrated all the material that we have learned in the earlier chapters, and we looked at what happens when you have a converging diverging nozzle connected to a reservoir. And this was very similar to what we did in earlier chapters, precisely chapter 3. So the reservoir has a standard reservoir pressure PR, which is the K, which is also happens to be the stagnation pressure for this flow through the converging diverging nozzle. That is until you encounter a shock, and once you encounter a shock, after the shock, the stagnation pressure is going to change. But as long as the flow is isentropic within the converging diverging nozzle, this is the stagnation pressure for that region to which it is connected. And so now you have this reservoir with a certain stagnation pressure, and then you have a certain nozzle whose shape is given in the form of the exit area to the throat area. So that's just the way people usually try to characterize the shape of a nozzle. So you have an exit area to a throat area, and then you have the back pressure. So these are the three control variables. So the PR, the AE by AT, or the nozzle shape, and PB. And sometimes people combine this PB and PR into a variable which is PB by PR. Okay, so in essence, there are three pieces of information. One is the nozzle design, there is the wire condition, and the condition on the back end, which is essentially the ambient atmospheric condition or the environmental condition into which this nozzle is emptying out fluid into. Okay, so that is where we are, and like as I mentioned in class, you can control any of these three parameters to dictate the flow conditions. In this case, we are going to control the back pressure, and that's what we discussed in class. So as we change the back pressure, so we start with the back pressure value equals the reservoir pressure value. So we start with PB and PR, okay, and this is AE. This is AT, okay? So you can have AE by AT, PB by PR are the control parameters. You want to split PB by PR, it's going to be PB and PR. So anyway, so if PB equals PR, there is no flow, and as we gradually reduce PR in a systematic fashion, you're going to allow a flow until PB is small enough that the flow is going to get choked at the throat, but high enough at the back end to support only a subsonic solution. So that corresponds to this case 4 that we talked about, which is the PB is small enough for Mach at the throat equals 1, but high enough for the Mach at the exit plane to be subsonic. And this is called as the subsonic choke flow solution, also called as a critical back pressure for this nozzle, right? I mean, this is the time, this is the value of the back pressure for which the nozzle, highest value of the back pressure for which the nozzle is choked. So this is what we learned in chapter 3. So nothing new here. And obviously, if you reduce the back pressure, and if you're still looking for an isentropic solution, so then there's another value of the back pressure corresponding to the same value of AE by AT, with AT equals A star, which means there's another value of the back pressure that corresponds to a supersonic choked flow condition, and that is called as the design condition for the converging diverging nozzle, also called, and the corresponding exit Mach number is called as the design Mach number, and the corresponding exit pressure is called as the design pressure. Okay, so that's the condition under which the nozzle is designed to operate typically. Okay, hence it's called as the design condition, and that corresponds to case 5. So this is case 5 that corresponds to case 5 in this diagram, which is the isentropic or the perfectly expanded case, and the flow is isentropic even though the flow is supersonic in the diverging section of this nozzle. So cases 1, 2, 3, 4, and 5 are covered in chapter 3, nothing new here. What we have added in chapter 4 is cases A, B, C, D, and E, these cases were not there in chapter 3. What we added, so these are cases that corresponds to back pressure values that are in between the values of PB corresponding to case 4 and PB corresponding to case 5. And PB corresponding to case 5 is a supersonic choke flow solution. PB corresponding to case 4 is a subsonic choke flow solution, also called as a critical back pressure. So A, B, C, and D are values that are of back pressure corresponding to conditions where PB is operating in the range of PB4 and PB5, and E is the case is an expansion case corresponding to a back pressure value that is smaller than the supersonic choked flow solution corresponding to PB5, okay, or corresponding to case 5. So if a back pressure value is smaller than that corresponding to case 5, then you encounter a situation under flow physics such as that observed in case E. Okay, so the unique thing about this case A, B, C, and D is all of them represent non-isentropic flow conditions. That's the first one. And the reason why they represent non-isentropic flow conditions is A, B, and C have a normal shock in the diverging section of a nozzle, and D has an oblique shock in outside the exit plane of this nozzle. Okay, the case E is what is supposed to be an expansion shock, but an expansion shock does not exist. It has no mechanism to form. So what we have is a gradual expansion wave, which is also called as a Prandtl-Meyer expansion wave. And case E, since it's gradual expansion and it's Prandtl-Meyer expansion, it can be considered as an isentropic process. So out of the 5 cases that we added in this chapter, 4 are non-isentropic. That is A, B, and C, and D. And the case 5, the 5th case, that is the case E, is an isentropic case. Okay, so that's what we have done. And we have so here I'm going to look at provide some caveats to the kind of analysis that we have done so far. So far, all the stuff that we have talked about is in the limit of 1D analysis or in the one-dimensional flow restrictions. And the basic idea is the following. The flow physics depends solely on the area ratios AE by A star, okay? And which means the nozzle length doesn't play a role. As long as you have the same area to throat ratio at a particular location, it doesn't matter what is this distance of separation between the throat and this exit area location or something like that. So, or in other words, the slope or dA dx is not important. Okay, so that is the essence of this 1D analysis. The other issues, such as what about influence of boundary layers on the nozzle design? So in these cases, in this textbook, we focus primarily on situations where boundary layers have no role to play, but in reality they do, which means you have to generate, look at 2-dimensional, 3-dimensional models, either theoretically or on the computers to understand the physics. Okay, so the question that is worth answering, and this is where we stopped last class, is under what conditions does a normal shock exist in a diverging section of a converging diverging nozzle? Well, so we looked at in total 10 cases, cases 1, 2, 3, 4, and 5, and cases A, B, C, D, and E, right? And out of these 10 cases, there are only 3 cases when the normal shock exists in a diverging section of a nozzle, and those correspond to cases A, B, and C. And here are some facts that tell you what those 3 cases represent. So the shock exists when, 1, the flow is choked. So the flow has to be choked, which means if a problem statement says that a shock exists, then it means that the flow is choked, okay, at that point. Then for a shock to exist, the PB, the back pressure, should be smaller than PB4. The PB4 is also the critical back pressure, which corresponds to the back pressure for the subsonic choked isentropic flow case. So that is your case 4. So this is the subsonic choked isentropic flow case, and your back pressure should be smaller than that subsonic choked flow case. Okay, and the back pressure should be greater than PBC, which is the case when the normal shock appears at the exit plane. Okay, so here in fact it should be greater than or equal to, right? Because when PB equals PBC, it represents a situation where normal shock exists in the diverging section of the nozzle. So PB should be greater than or equal to PBC, which is the case with normal shock at the exit plane. Okay, and I'll tell you how to compute these two values for a given nozzle. So for a given nozzle, say a given AE by AT comma PR. Okay, so we have given these values, then how to compute this PB4. So the PB4 can be obtained with the knowledge of AE by AT. So right, so the flow is choked, so AT is the throat area is also the same as A star, which means you can look into isentropic flow solutions or appendix B in your tables, and you can find, okay, say AE by AT is 2, then you can compute what the two roots are for that value of AE by AT. One is going to be a subsonic flow solution, another is a supersonic flow solution. So you choose the subsonic solution for ME from appendix B. And then the corresponding value of PE by P01. This is isentropic flow, so there's only one value of P0, right? So the PE by P0 that corresponds to that value of ME is nothing but PB4 by P01. And if you know P01 is PR, so if you know what your stagnation pressure is, you can get your PB4. Okay. Now the next part is how do you compute your PBC, and which is the other extreme limit, when if PB greater than or equal to PBC, then the normal shock exists in the diverging nozzle. So this PBC can be obtained as follows. So what you have to assume here is you have to assume that a shock exists at the exit plane, and you want to compute what the Mach number in front of the shock is. And for that, I know what AE by AT is for that shock location. And since the shock exists at the exit location, the area of cross section at the exit plane is AE. So the Mach number in front of the shock is given by the isentropic flow solution, right? So AE by AT gives you a value of ME, and P1 by P01, or P1 is the value of the properties right in front of the shock. So it's going to be, so AE by AT is going to give you M1 basically, okay, and which is the same as ME. It's going to give you M1, and say AE by AT is 2, then M1 is say going to be something like 1.7 or 1.8 or whatever value it is. Then you get that value from appendix B, compute P1 by P01. And this is the Mach number in front of the shock. Now you apply shock tables to get M2 and P2 by P01. And since the flow behind the shock is subsonic, okay, so P2 by P01 is provided, okay, in appendix C. If not, it is nothing but P2 by P1 times P1 by P01. That's how you get P2 by P01, right? And since the flow behind the shock is subsonic, P2 equals PBC, so all you need is to find what is this P2, okay? So therefore P2 equals P2 by P1 times P1 by P01 times P01, which is nothing but PR, okay? So this is how you get P2. So this is how you compute the range of back pressures over which the normal shock exists, okay? So here's an example problem, which is our example 4.4 in your textbook, and I'm going to go over this problem. It's quite simple, okay? It's a converging diverging nozzle that is designed to operate at an exit Mach number of 1.75. The nozzle is supplied air from a reservoir at 5 megapascal. Assuming 1D steady flow with gamma equals 1.4, calculate the following. Okay, the maximum back pressure to choke the nozzle, what is that? That's your PB4, right? Which is PB critical, okay? The range of back pressures over which a normal shock will appear in the nozzle, so it's PB less than PBCR greater than or equal to PBC, okay? The back pressure for the nozzle to be perfectly expanded to the design Mach number, so this is PB5, okay? And the range of back pressure for a supersonic flow at the nozzle exit plane, you can check supersonic flow will exit at the nozzle exit plane for all the cases with back pressure less than C, which means once the normal shock exits from this diverging section, the flow at the exit plane is going to be supersonic, even though there's an oblique shock, but the oblique shock exists. But the oblique shock exists only outside the nozzle region, so it's going to be PB less than, not less than or equal to, it's going to be PB less than PBC. Okay, so this image that I gave you as a handout, which is all these nice colorful plots of the pressure distribution for different cases, is actually a very useful and very important image. It allows you to understand the physics and solve a lot of the problems. Okay, so obviously, like always, we'll draw a schematic. So the reservoir pressure is given as 5 megapascal. We assume a shock exists, but but that's just for representation purposes. Design Mach number, so your ME is 1.75, okay, and gamma equals 1.4. So the design Mach number is essentially the Mach number that you would get if the nozzle is operating under design conditions. And what is design condition? A nozzle is designed to operate for supersonic isentropic choke flow solution. Okay, so this ME is nothing but ME corresponding to case 5. Okay, that is so if I know ME, then it is nothing but the supersonic solution corresponding to the value AE by AT for that nozzle. So, which means if I know ME is 1.75, I can get AE by AT. Or if I know AE by AT, I know the design Mach number, and also know the subsonic flow Mach number. Okay, so this ME equals 1.75 is equivalent to specifying the nozzle shape. So obviously all the assumptions, you need to list them out. 1D steady isentropic flow, except shock and adiabatic. The shock is adiabatic. It's a stationary normal shock. It's a perfect gas. Okay, what is the information that is provided? PR is 5 megapascal, gamma is 1.4, R is 287. So if it's not provided, you can assume this value. The design Mach is provided. ME is 1.75. And you have to understand, okay, what is the PB for the different conditions? So all you have to find out is, let's see, PB4, PB5, PBC. Okay, so you have to find 3 PBs, okay, in total. So you have to find PB4, PB5, and PBC. Okay, so it's such an easy thing to do, right? I mean, if I know my P naught and PB4 or PB5 and PB5 are isentropic cases, and I know my ME5 or ME, which is 1.75, which means I can go to my appendix B, compute AE by AT, and for that value of AE by AT, I can get my PE by P naught. That is going to be my PB5. Okay, and once I know my AE by AT, I can compute the corresponding subsonic choke flow solution. That's going to give me another PE by P naught, and that PE is the same as my PB4, which is the subsonic choke flow solution. And once I know PB4 and PB5, PBC we can obtain as we discussed a few minutes ago. Okay, so let's compute maximum PB to choke the nozzle. That is the first part of the question. So this is basically PB4, which is also the same as PB critical, okay, which is for this happens when the flow is choked, an isentropic and subsonic in the diverging section of the nozzle. So the design Mach number is ME equals 1.75. So from that you get from appendix B, you can get AE by A star. Since the flow is choked, A star equals AT, so this is AE by AT. And for ME equals 1.75, the AE by AT is 1.3865. So this corresponds to the supersonic case. So you can compute the corresponding subsonic solution for AE by AT is 1.3865, and the subsonic value of the exit Mach number is 0.48. And so the PE subsonic by P naught is 0.8541, and my P naught is 5 megapascal. So I can get my PE subsonic as 4.27 megapascal, which is also my PB4 or PB4 or PB critical. So it's 4.27 megapascal. The range of back pressure for which a normal shock will appear in the nozzle, the normal shock will appear for PB less than PB critical. So you need to look at that image handout that I gave you for the stationary normal shock in a converging diverging nozzle. So the PB critical is already been computed as 4.27 megapascal. Now I can do PB greater than or equal to PB subsonic behind the exit shock plane, which is PBC, right? So I need to compute this PBC, which means I need to look at a case where at the exit plane of this converging diverging nozzle, I have a shock that is given in red. So this is my shock, okay? So this is my shock, and I can denote the conditions before and after the shock by 1 and 2, okay? So the Mach number at the location in front of the shock is the isentropic flow solution at that location, right? Because the flow here is isentropic, okay? This is isentropic flow, right? This is isentropic flow 1, okay? So if it's isentropic flow 1, then the Mach number at this location just in front of the shock, which is also the exit plane, is given by a corresponds to the isentropic flow solution for AE by AT equals 1.38 whatever 75, which is also the design Mach number, okay? So and so your M1 is 1.75. Now I can do use appendix C to compute. And for the corresponding value of M1 equals 1.75, the P1 by P01 from appendix B is 0.1875. So now, this is Mach number in front of the shock is 1.75. So I can use appendix C to compute P2 by P1, which is 3.40 for M1 equals 1.75. And the corresponding Mach number behind the shock is 0.6275. So the exit plane pressure, the flow behind the shock is subsonic. And since the flow behind the shock is subsonic, the exit plane pressure is the same as the back pressure. So your PE equals PBC, that is what you want to compute, is also this value P2, which is the, because there's not, the exit plane is now the region behind the shock, right? It's exactly at the location behind the shock. So your PE equals P2 equals PBC, which is, and how do you compute this P2? You write this as P2 by P1 times P1 by P01 times P01. Okay, so and I already know P01. I know my P1 by P01 as, so this comes from here, and my P2 by P1 comes from here. So I do all of this and I compute the value, which is 3.1875. So I'll have a shock, normal shock in the nozzle when my PB is greater than or equal to 3.1875 megapascal and less than 4.27 megapascal. Now the last part of the question, find the PB for the nozzle to be perfectly expanded, right? That is easy. The perfectly expanded case means you have some, it's a supersonic isentropic choke flow solution at, when this happens, the exit plane Mach number is supersonic, and since it's perfectly expanded, even though the supersonic flow cannot sense the back pressure, the exit plane pressure and the back pressure are the same because it's perfectly expanded. Okay, which means I know my design Mach number. All I have to do is go back to my appendix B, my isentropic flow solution, and compute my PE by P0, which is the same as PB by P0. So that's what I'm doing here. So my exit Mach number or design Mach number is 1.75. My PE by P0 corresponding to that supersonic flow solution is 0.1875. So my PE is 0.9375 megapascal, which is also my PB5, which is 0.9375 megapascal. Okay, so that is what I want to compute. So this is the PB for the perfectly expanded nozzle, and the range of PB for supersonic flow at the exit plane. Supersonic flow at the exit plane will occur when PB less than PBC, which is 3.1875 megapascal. So this is how you would solve the problem. So knowing this sheet, which is let's see, which 45, right? 44. So knowing this this chart in page 44 intimately is actually critical to solve a lot of these problems in this chapter. Okay, so I want you guys to spend some time looking at this situation, right? I mean this information. Okay, so this is we have done one example problem. There are other example problems that we'll try to solve maybe a little early next week before the exam. Okay. Now the next part of this problem solving is the following. So we need to identify what is called as the location of a stationary normal shock in a converging diverging nozzle. This is kind of the flip version of the problem that we have solved, right? So far what we have looked at is, okay, I give you AE by AT or the design Mach number, and I give you PR, which is the reservoir pressure. Now compute the PB that is required for a shock to exist at a certain location. That's how we have done solved problems so far. Now we are going to flip the problem. Now we are going to say, I'm going to give you AE by AT, the shape of the nozzle again, and I'm also going to give you PR. But now, in addition to PR, I'm going to give you the back pressure. And you have to compute where the shock is going to be, okay? So that is this section of this chapter. And we can consider a converging diverging nozzle containing a stationary normal shock. The problem statement is the following. So given nozzle shape AE by AT and operating conditions PB by PR or PB by P01, find the shock location AS by AT. So this is the problem statement. And the first approach is to do exactly what we have done so far, but do a reverse engineering approach, right? So what did we do so far? We were in the previous example problem, we were saying, okay, we're trying to identify what is the range of back pressures for which a shock could exist somewhere in this location. Now we are going to do the reverse. So what we're going to say is, this is the back pressure, so where would the shock exist? And to do that, what we have to do is, the first approach is what is called as trial and error. So if you assume a shock exists at a certain location with a cross-section area AS, which gives you AS by AT, right? The shock would exist only when the flow is choked, which means AS by A star would correspond to AS by AT, okay? Is assumed and specified. So you start with the initial guess, and then you would assume, imagining a shock is existing at that location, you'd solve for static and stagnation properties for that given value of AS by AT. That is, what is the back pressure? If a shock exists at a certain location, say, then what is the corresponding back pressure or the exit plane pressure? And if the resulting values of the exit plane pressure does not match or does not make sense, what sense means here is that if it does not match the corresponding value of the back pressure, then we have to move the shock either to the left or the right to adjust its position so that the back pressure values are matched. So then we'll choose a new location of the shock and repeat steps 1 to 3. So this is an iterative algorithm, okay? So this is iterative algorithm. So this is the iterative algorithm. And then after you do a few iterations, the final shock location doesn't change by a certain value. Say in one case, AS by AT, you start with AS by AT equals 2, 2.5, 2.51, 2.512, right? Then you kind of stop at this location or this location, depending on your tolerance, and say this is the final shock location. So it's an iterative solver, okay? The detailed way of doing this iteration is the following. So you assume a value of AS by AT, which is A1, which is the area of the location in front of the shock, divided by A1 star, where A1 star is the A star for the isentropic flow region in front of the shock. From this, I can get, if I know my AS by AT or A1 by A1 star, I can get my M1, right? My Mach number. And once I know my Mach number in front of the shock, I can solve for the shock jump. Using appendix C, it's going to give me P02 by P01. And once I know P02 by P01, I can get A1 star by A2 star, okay? And now I can compute AE by A2 star. Okay, AE by A2 star is nothing but AE by A1 star times A1 star by A2 star, which is AE by AT times P02 by P01. And this is provided, this is computed here, okay? So now I can get AE by A2 star. And if I know my AE by A2 star, I can compute ME from appendix B. And once I know ME, I can get PE by P02, okay? from appendix B. Okay, and once I know my PE by P02, we need to compute PE by P01 or PE by PR, right? Because your PE is the same as PB for subsonic flow behind the shock. So this is going to be PB by PR. And the way you compute PE by P01 is PE by P02 times P02 by P01. And P02 by P01 is already computed from step 2, right? So P02 by P01 is computed from step 2, and P by P02 is computed from step 6. Okay, so this is which means you can get P by P01 or P by PR, and if this P by PR is the same as PB by PR. So if this value is smaller than the specified or the given value, say if my PB by PR is 0.8 and my given value of PB by PR is 0.9, okay, then it means my shock is too far downstream, so I have to move the shock upstream. Okay, and for this you have to understand this plot on page 44. So here you can see, right, so as you decrease the back pressure corresponding to cases A and B, the shock moves downstream, right? So if the back pressure value is you're computing a back pressure value that is lower than what it should be, then you should move the shock to the left. Okay, if you're computing, so what you're essentially doing is you're under predicting PB, which means you're computing the case corresponding to case B. Okay, whereas what you're really supposed to find out is the case corresponding to case A, which means you need to move the shock upstream. Okay, so you use that piece of knowledge, let's see, yeah, and then you move the shock upstream. That is, if the given back pressure is higher than the computed value, then if the given back pressure, that is the specified back pressure, is higher than the computed value, then move the shock upstream. Or if the computed PE is greater than the given PB, then you move the shock downstream. Okay, so if the specified value is a smaller value and you're over predicting the PB, then you need to move the shock downstream. Okay, and once you do this, so what you can do is you can do this by trial and error. There is a way to get your new shock location as a fraction of the old shock location. Okay, and you can use this formula if you're writing a program. Okay, so this approach typically requires only a very few iterations. Okay, it's not that complicated, but there is a more direct approach. There is a direct analytical estimation of the shock location, and the way to do that is the following. So you consider the back pressure to reservoir pressure ratio. So this is provided, right? And this PB by PR is nothing but PB by P01, and if there's a shock in the diverging section, then the flow behind the shock is subsonic, so your PB is the same as PE. So this is equivalent to PE by P01. This is nothing but P by P02, which is P02 is the stagnation pressure for the isentropic flow behind the shock, times P02 by P01, which is the ratio of the stagnation pressures that you get from appendix C, right? This is nothing but P by P02 times A1 star by A2 star. Okay, and this P by P02, so if P is the exit pressure, P02 is the stagnation pressure behind the shock for that isentropic flow behind the shock. So which means my P by P02 can be written purely as a function of the exit Mach number and gamma, correct? And A1 star by A2 star can be written as A1 star by AE times AE by A2 star, right? So this AE by A2 star is also can be written as purely as a function of Mach number, exit Mach number at that location, AE and gamma. So the only term that needs to be identified is A1 star by AE, but if there is a shock, the flow is choked, right? So which means A1 star is nothing but AT. So this is AT by AE. So this is, and which means A1 star by AE is AT by AE, or AE by A1 star is AE by AT. Okay, and this is given. This is given, and the left hand side is also given. This PB by P01 is also given. So the equation that we are having, so you can figure out what that f of ME is. There is nothing but 1 by 1 plus gamma minus 1 by 2 ME squared raised to gamma by gamma minus 1. AE by A2 star can also be written as ME, and this is the expression. This is the expression, this is basically the G of ME term, ME comma gamma term, okay? So you plug these expressions for ME and you get this form of this equation. So this is your equation 128, okay? So modified form of 128, okay? So that is what we are doing. So this is a modified form. So my PB by PR is nothing but some function of ME and gamma times AT by AE. So I can bring that AE by AT to the left hand side. So it's going to be PB by PR times AE by AT, and the right hand side is going to be purely a function of ME and gamma, okay? So the left hand side is known. This is given, and this is also given. So right hand side is a function of ME, and ME is what you're trying to solve for. So you can write an equation for ME in terms of known quantities. So this is equation 129, and if you square it, it turns out to be a quadratic in ME squared, which you can solve easily, and this is the solution. So this is the final solution. This is the solution for ME, okay? So now if I give you my PB by PR and my AE by AT, which is, if I give you the ratio of my back pressure to my reservoir pressure and my AE by AT, which is the nozzle shape, another way of giving AE by AT is to give ME directly, okay? For ME directly for the supersonic isentropic flow solution. But here, we don't have a supersonic isentropic flow solution. We are assuming a shock exists, and we are going to see whether a shock can exist or not. And so what we're doing is, so this ME, so if I know my AE by AT, I'm computing the corresponding ME for a shock for a given value of back pressure, and this is the expression. So this is the expression for ME, and once I know my back ratio of back pressure to reservoir pressure, P by PR, and my AE by AT known, these are known, right? So I'm going to plug these into this expression, and then I'm going to compute my ME. And once I compute my ME using this equation 131, once I know my ME, I can get my PE by P02, right? That is my local, from my isentropic flow solution, or appendix B, I can get my local ratio of static to stagnation pressure, okay, for that value of ME. And now, the nozzle exit plane is behind the shock, so PE is the same as PB, which means PE by P02 is PB by P02, which is PB by P01 times P01 by P02, right? So this PB by P02 it was just computed in step 2, okay? Right? And I'm sorry, this is not the way to... So this is given as PB by PR, okay? This is given, this is computed from step 2, which means I can get P01 by P02, right? And P01 by P02 is nothing but my drop in stagnation pressure across the shock. So I can go back to my appendix C, I can take this value of P01 by P02 from the step 3, okay, from here, and find, this is the jump in stagnation pressure across the shock. So I can use my appendix C or my shock tables to compute the Mach number M1 in front of the shock. And this M1 obviously will be greater than 1. Okay, use that corresponding solution. That is the supersonic solution for M1. And once I know my M1, my M1 is the Mach number at the location in front of the shock, and that I can compute the location of this M1 by using appendix B to compute AS by A1 star, where A1 star is the reference area in front of the shock, and since the flow is choked in front of the shock, A1 star equals AT, so this is AS by AT, which is the expression that we are after. So we can find the location by knowing the Mach number in front of the shock. Okay, so in this equation 131, okay, in this equation 131, the ME squared is always greater than 0, okay? So that is an observation, so which means you will never get an imaginary solution. It'll always be a positive real solution, okay? So let's apply this expression to a simple problem. So PB by PR is provided as 0.7 for a converging diverging nozzle. AE by AT is 2. Determine the shock location for gamma equals 1.4, right? So all you have to do is to draw a control volume, draw a converging diverging nozzle, draw 3 different control volumes. Control volume 1 is the isentropic flow solution. Okay, so let me draw the this is isentropic flow 1. This is shock. Okay, the control volume 2 is the shock control volume, and this is isentropic flow 2. Okay, obviously assumptions: 1D steady isentropic flow, shock is adiabatic, caloically perfect gas, and PB by PR is provided as 0.7, AE by AT is 2.0, gamma equals 1.4 to find AS by AT. Okay, so you can solve it 2 different ways. If you really want some practice, I suggest you solve the the iterative approach. Okay, so out of class assignment. Use iterative method. Okay. Okay. In class, since we are trying to save time, in class, so we'll just solve this solution. Step 4. Okay. So we are going to use the actual expression. So let me write down the solution. Okay. So this is an important problem. Okay, so the first part is you have to make sure shock exists. Okay, in all these kinds of problems, you need to make sure shock exists in the first place. Okay, and how? Right. So for shock, we solved this problem early in this lecture, right? For shock to exist, that is, okay, let me be precise, okay? For normal shock to exist, PB less than PB4 equals PBCR greater than or equal to PBC. Okay, so this is what we need, right? And we have to compute. So this is the case with normal shock at exit plane. You have to make this check, okay? Whenever you have a problem where you have to find the shock solution, you have to make sure shock exists. If the problem says assume the shock exists, don't worry about verifying it, then you can go ahead directly and compute the shock location. But if it is not specified explicitly, then you need to verify, okay? That is important. And obviously there'll be points associated with the steps to verify the existence of a shock. So this is the subsonic isentropic flow solution. Okay, so how do you compute for how do you compute this PB4, right? For AE by AT equals 2.0, isentropic subsonic choked flow solution is given by appendix B. Obviously you have to look at the subsonic solution. So ME equals 0.31, which implies PB by PR equals PE by P01 equals 0.9 equals PB4 by PR equals 0.935. Okay? Okay? Okay, so now we have to compute PBC. Now compute PBC by PR, right? Which corresponds to, let me write it this way, corresponds to shock at exit plane. So if this is the converging diverging nozzle, and this is the shock at the exit plane, let's call this as 1, 2, then M1 is from appendix B So you need to look at the supersonic solution for AE by AT equals 2. Okay, this happens to be 2.2. Okay, 2.2 equals M1, which implies M2 equals ME, because the shock is at the exit plane. So just behind the shock you have exit Mach number. So you have subsonic flow of 0.547 PE by P02. I'm sorry. P02 by P01 equals 0.628. P2 by P1 equals 5.48, and P02 by P1, okay, is 6.716, or 716. Okay, so this is the values that I get from my appendix C. So let me box these values up. So this is the value from appendix C. For M1 equals 2.2. Okay, so what we are after is PBC, right? PBC by PR equals PBC by P01, which is PE by P01 equals P2 by P01, which is P2 by P1 times P1 by P01. So which is nothing but P2 by P1 times P1 by P02 times P02 by P01. So I'm using, you can directly compute this, but I'm computing these values. I think I already have P1 by P01. Let me check. Probably not. I should have looked at it from here I could have obtained P1 by P01 directly, but since I did not do it, I have to do it the slightly longer way. And since I have P1 by P02 and P02 by P01, okay, I have P02 by P01 here. This should be P01. This is nothing but 5.48 times 1 by 6.716 times 0.628. This is nothing but 0.5125. Okay, so PBC by PR. So this is my PBC by PR. Okay, so now after all this, what is the use, right? So the given value, therefore, let me write it this way, right? So which implies that normal shock in diverging section exists for PB by PR less than 0.935 greater than or equal to 0.5125. Okay, this is for this given value of AE by AT. Okay, now let's compute the rest. So now for PB by PR equal to 0.7, from this a shock would exist and where, so use equation 131 to get ME. So the equation is ME squared minus 1 by gamma minus 1 plus square root of 1 by gamma minus 1 squared plus this extra term 2 by gamma minus 1 times PR by PB whole squared AT by AE squared 2 by gamma plus 1 raised to gamma plus 1 by gamma minus 1. You take this really crazy expression, plug in all the numbers, which you get ME equals 0.4067. So this is the Mach number behind the shock at the exit plane. From this, you can use Appendix B. You can get PE by P02 equals PB by P02 equals 0.8956, and AE by A2 star is 1.59. Okay, so you compute these guys. Okay, so now PE by P02 equals PB by P02 equals PB by P01 times P01 by P02, which implies that P01 by P02 is 0.8956 divided by PB by P01, which is nothing but, which implies P01 by P02 equals 0.8956. This PB by P01 is the same as PB by PR. Okay, so you have to make that connection. So this is PB by PR, which is 0.7, okay? So this is 0.7, so P02, or P01 by P02 is, this happens to be 1 by 0.79, okay? So if you do, okay, let me write it this way, which implies P02 by P01 equals 0.79, okay? From this, you can use appendix C in an inverse fashion. So appendix C gives you M1 for the given value of M1, P02 by P01, right? Now you know P02 by P01. Now you this implies, gives you from appendix C, M1 equals approximately equals 1.87, and for M1 is 1.87, which location in the isentropic flow region 1 would M1 be 1.87? So this, from this you use appendix B to get A1 by A1 star equals AS by AT, which is 1.51. This is the essential method. So this is how you do it. Okay? So this M1 is the Mach number in front of the shock. So which location in the isentropic flow region 1 would give you this Mach number, and for that you have to use appendix B, and you get A1 by A1 star is AS by AT is 1.51. So in the textbook there is other problems, 4.24. Here it's the same problem. The question is PB by PR is 0.7, the same value that you just used. AE by AT is 2.0, and your gamma is 1. So here instead of gamma 1.4, you're using gamma equals 1.3 and gamma equals 5 by 3, which is 1.67. So the question is, for different values of gamma, what is the shock location? Draw a conclusion regarding the shock location and gamma. So I think this is off class assignment for you guys, so I hope you guys can work it out. So all you have to do is follow the same procedure that we just did. You can assume that the shock, in principle, you have to, for this different value of gamma, you have to compute what your range of back pressure values for which a shock would exist, okay? But since these, but let's assume for the time being that the shock is going to exist, okay? Just to save your time. But if you really want to verify that, you should. And in a real exam type setting, unless and until specified, you have to do that. Okay, so you first have to verify whether the shock would exist for that value of gamma, and once the shock, you know the shock exists, you can find the shock location. So you have to compute the shock locations, and you'll observe that you'll have different shock locations for for gamma equals 1.3 and gamma equals 5 by 3. So you'll have different shock locations. And you can actually try to identify a trend in terms of how the shock moves or shock location changes as a function of gamma. Okay, so why don't you do this as an off-class assignment, and we'll discuss the results. So I'll put the solution key later on and upload a complete version of this filled up notes for this chapter. Okay. So I think with that we pretty much complete this chapter. There's a little bit more discussion on diffuser flows. The basic idea of a supersonic diffuser is you have the aircraft is traveling at supersonic speeds, so you have air that is coming in. So this is mainly an application in terms of what is called as air breathing propulsion. So you have supersonic flow coming in because the flight is moving at supersonic speeds, and combustion cannot happen at supersonic speeds, okay? So some combustion, the flow needs to slow down. And the key idea of a diffuser is to slow down the flow such that you retain all, if not most of the energy, okay? I'm sorry, most if not all of the energy, okay? And the way you do that is by avoiding a shock, because the moment you have a shock, especially if it's a very strong supersonic flow coming in, you create a shock to slow down the flow, you're going to waste a lot of the energy and lose a lot of the P naught that is inherent there in this flow, right? So you want to, because you want to energize the flow, right? So the way you generate thrust is by pushing this flow, right? So now if you take in flow with huge amount of momentum, then you waste a lot of the momentum by creating a shock, and then you have to put all that momentum back to push to generate thrust. If you cannot do that, you're not going to be able to generate thrust. So, which means you have to burn more fuel to do that. Okay, so the way the supersonic diffuser works is it tries to identify a method by which you can slow down the flow efficiently without losing much of the energy, and then you allow the combustion process to happen, increase the energy content in the flow, and then you push it back again through a converging and diverging nozzle like this and accelerate the flow, and you have a higher Mach number at this exit plane. So this is going to be m, say much greater than the value that is mi. Okay, and which means now you're having higher momentum, fluid getting thrown out, which means thrust is going to be generated. So that is the essential idea of a converging diverging supersonic diffuser. So what I'll do is I'll spend another 5, maybe 15, 20-minute lecture at most as a follow-on section to this current one, and I'll post it on YouTube in the next day or two. Okay, all right, thank you.